Okay, so after my PhD I went into industry, as I mentioned, and went into the design world of the upstream oil and gas industry, and then developed some software for assisting companies in the design of these upstream facilities. So I thought I'd pass on some of my wisdom and perhaps some of my mistakes in this next 20 minutes. I'll just introduce the upstream oil and gas industry, for those of you who are not familiar with it, and then talk about the length scales of the problems involved, the kind of problems that we need to solve, and some of the time scales that we've got to solve it. And so therefore the requirements of some of these simulators. Well, the upstream oil and gas industry starts with reservoirs of hydrocarbon and can have oil, water and gas in there, captured underground with mechanisms I won't explain, because I don't have a beard and I'm not a geologist to explain how these things have come about. But what I'm involved with is the design of the extraction system of these, starting off with wells that are drilled into that reservoir, and then in this case it's a subsea oil field tied back to some processing facility by a pipeline. No matter what phases that comes in here, it just so happens multiphase flow occurs at some point as you're going along this system, thanks to the wonders of thermodynamics and the multi-component system it is. Okay, and then at some point it's exported to a refinery and then turned into plastic and asphaltene and petrol and all that stuff. Okay, so this is the stuff. This is the area that I'm mostly concerned with, and most of my comments are really about this industry rather than this is more generic chemical engineering, still with multiphase flow in there and heat exchangers and things like that. Talk about length scales. Pipelines are long bits of metal with a hole in it, and that diameter of this is in order of hundreds of millimeters. With that, okay. The problem is the lengths can be hundreds of kilometres. Okay, so put that in perspective. That's where you are now, and that's St Andrews. That's just over 100 kilometres. So that's just to help you imagine 100 kilometres we've got. So the problem is the length can be hundreds of thousands of times longer than the width and the height. So it doesn't naturally lend itself to the CFD simulation, particularly as we want to model the whole pipeline, because things are changing along the length, the elevation's changing, the number of phases that are present can change, the temperatures, the physical properties, flow regimes, things like that can change along the length. So I really do need to model the whole length. I can't just model 1 metre of this and extrapolate. So as I say, it doesn't lend itself nicely to CFD simulations. It's typically what we call 1D models. If you're familiar with that, good. If you're not, I'm not going to explain it to you. I don't have enough time. The kind of problems that we need to solve this is the classic one, this is the most important one really, is how much will I make? This is a good engineering problem. I know how much I will spend on pipelines and wells, but how much money will I make? And it's dictated by the reservoir pressure, so we know the inlet pressures, and we know the outlet pressures, and we want to know what the flow rate is. I don't know what the inlet flow rate is to my system. It's dependent on what I put in between. If I put a pump in here, I'll get a higher flow rate. If I make a bigger diameter, I get a higher flow rate. So to back calculate that pressure, of course, I know this pressure here, I know the outlet pressure. To back calculate that pressure, for example, I need to know what the flow rate is and the physical properties of that, all the different phases, etc. But to get that, of course, I need to know what the flow rates are. Those are a function of that. So it's an implicit system. I need to calculate the flow rates and the pressures at the same time. It's well posed, but it's just an implicit. There are an easier system to model, which is if it was flow rate specified. If somebody told me there were 5,000 barrels a day from here and 10,000 barrels a day from there, and I knew what composition was, then it's simple maths to work out what the composition of this is. I know these compositions. I know that I've got twice as this, and I've got that. It's all quite straightforward. And then I can back calculate what the pressure is. That would be simple. But to do that, when you're calculating the compositions and pressures and flow rates at the same time is difficult, but it adds a lot of value to the design, because I want to know what if this is an 8-inch pipe or a 10-inch pipe, what if it's got a pump or not a pump, various other scenarios, and I want to know how much more will I make from that system. Other problems, flow assurance. This is a term originated from Petrobras, and that's what it is in Portuguese, but I'll call it flow assurance. They were the kind of pioneers of this, lumping this together. And really, it's lots of hydraulic issues such as liquid slugs and surges and things like that, but also solid phase issues such as hydrates, wax, asphaltenes. These are solids that can precipitate in the pipeline. Here's an example, a nice picture. Everyone showed when they do a flow assurance presentation, they show a picture of some black gunk coming out of something. And this is some wax that fortunately have come all the way through the pipelines and arrived in a vessel that they could clean out. But if you can imagine if this big lump of solid gunk was actually 1 kilometre down and 5 kilometres that way in a pipeline, it's much harder to actually get to and clear out. And that's the problem, we want to avoid that. Other problems here are lumped together called integrity management, and that is a catch-all term for anything that any engineering to avoid a rupture in the pipeline. Okay, so here's a little animation of someone doing something, but this is including corrosion, which is chemical reaction with the steel and nibbling away at the wall. Erosion, this is flow wearing down the pipe, but also some pipeline mechanical issues, which are shown in some of these videos here, of the pipeline caused by the pipeline warming up and the metal expands, it can pop out of the ground, and then as it cools it contracts, keeps doing that and causes all kinds of stresses on the pipelines. So flow assurance guys don't get involved in doing those calculations usually, but we do get involved in giving them temperatures and pressures and compositional information for their calculations. So optimization is another problem that we need to solve. Optimizing during the design, as I mentioned before, it's an economic decision to size a pipeline. If you select a bigger pipeline, then you'll get more flow rate in general. There are subject to caveats there of increasing slugging and things like that, but the more money you spend, the more you will get. And what's the trade-off between that? The cost-benefit analysis of that. And we don't just want to optimise it for day one or the first year of production. We need to optimise it for the whole life of the system. And the system will change as the reservoir depletes, drops in pressure, changes composition as it's generated throughout life. So many life of field simulations need to be run to see where you're operating this model, the way it would be operated in reality, normal operation. But to optimise, we also need to optimise how we're operating this thing in our model. So we need some sort of production optimisation during this model. To model normal operation, we must know how they would normally operate. So normally operate to optimise the value, I presume. The operators that I've met like to think that they are making a good choice whenever they're operating the system to maximise the value of this asset. This could be as simple as producing as much as they can, but that is subject to I may be doing some damage to the reservoir that would cause me to not produce as much next year. There may be some constraints on that optimisation. So each of our normal operating simulations should be optimised as it would be in reality, as the way that we're operating at each point in time, each time step. Now, because reservoirs don't change that quickly, normally it's like once a month we have to change the choke settings or the pump settings or the compressor settings of this system in order to operate in a more optimal fashion. So let's have a look. I've got a nice simple system here. This is a 7-well system and all into the same tieback. This is the production profile. Different colours here are the oil flow rate from different wells. This is time along this axis. You see that we've got a drilling schedule until we meet our desired 60,000 barrels a day, and then at some point we drop off plateau because the reservoir has lost its pressure or some other reason for why we can no longer maintain production rate. Now what we want to optimise will change through life. In early life, it's a drilling schedule optimisation. I've got 7 wells. I can only drill them one at a time because drilling is expensive, and drill rigs, there aren't that many of them, at least not in offshore systems. So if you work it out, we've got 7 wells, and you can drill them in any order. There are 5,047 factorial different scenarios, just for that bit there. Right. It gets worse because in this what I'm calling midlife, where I've hit the processing constraint, if I open up all these chokes, I can produce a lot more than 60,000 barrels a day, but I don't want that. I can't do that. Contractual reasons or whatever, some constraint on something. Okay? I only do 60,000 barrels a day. So I have to choke back these 7 wells, but how much do I choke them back? Now, do I choke them back evenly? Well, some of them are producing more water than others, so they're not adding as much value as some of the other ones. What we call an allocation optimization. How much do I allocate to 60,000 barrels a day between my 7 wells? It changes through time because the productivity of these wells change, their compositions change, the value that they are adding is changing. If you work out the number of options that there are here, there's 7 chokes, and each choke has got 150 settings typically. That's from fully closed to fully open, and the operator decides, oh, today I want you to be at setting 57, and you to be at setting 43, and etc. Okay, so there are 150 settings. There's 1.7 quadrillion, there's 150 to the power 7 different scenarios at each point in time. Every month I've got to work out which of these 1.7 quadrillion different options there are. Similarly, similar kind of things can happen in late life, where I still can do some optimization on compression and lifting and how I'm using pumps and things like that in order to improve the production. But I've only got a limited resource, and how do I allocate this resource, electrical power or gas lift or whatever it is, between my wells to produce as much as I can, or add as much value as I can in a more generic sense. So these numbers add up quite a lot. That was just a simple 7 well example. Well, if we take that example, when it was 1.7 quadrillion, there's 7 wells. Of course, we have systems with many, many more wells than that. That's quite a modest size tieback. They can be, well, in certain systems, they can be in the thousands, but they certainly can be in the many tens of wells. And these add up. This is a log scale of the number of possible settings, from the sublime to the ridiculous, from the all fully open, all fully closed, and everything in between, all different scenarios. Quickly, just to put that into scale, that's the number of grains of sand on Earth. Okay, so that's quite a lot. I'm saying, of all the grains of sand on Earth, tell me which one's the best. Go out and find the best one. Okay, and then that's only about 10 wells. Okay, if I've got about 25 wells, that's the number of atoms in our sun, approximately. Okay. That's the number of atoms in the observable universe. These are big numbers. So I won't go into optimization methods, and whether it's a local optimum or whatever. But the bad news is, it's practically impossible for you to find the optimum. I'm sorry about that, it's impossible. The numbers don't lie. Okay? The good news is, it's practically impossible for someone to prove that found the optimum. So you've just got to stare them out. Stare them out. Okay? No matter how many they talk about so many quadrillion, you just go, the optimizer says it's optimum. Send that to them. Okay? So stare it out, people. So in the industry, what we, this is one of the things I didn't like in the industry at the time, in my early days, but I've learned to live with it. They talk about optimization, and I suck my teeth and say that's not optimization. What they mean by optimization is making things a little bit better in a reasonable time frame. That's what they mean. That's optimization, and they're quite happy with, you can boost production by 5% by doing nothing. Okay? Oh, you're a hero. The trick is the next year to come back again and try and, you can't keep increasing production by 5%. Not magic bullet, but still. So that's what I mean by optimization. It's a different mindset. So I'm talking about the Newton-Raphson method and all different methods for optimization. Is you can think simpler and still get a happy client. You don't have much time to solve these things, but I'll come on to that. Another big problem is uncertainty. So here's the challenge for any of you going into the oil and gas industry. Okay, on average, said in an International Journal of Petroleum Technology, someone had done the maths on new developments between 1999 and 2012, and they said that on average, only 60% of the promised value is delivered. So on average of all the projects. So you think if you're unlucky, and sometimes you're lucky, sometimes you're unlucky, and you cancel these things out. That on average, they're about right. But on average, we are always over-optimistic in the oil and gas industry. Still, it makes a load of money. That's how silly it is. It's silly lucky, the oil and gas industry. So they promise, 100, and they only give you 60%. But still, these oil and gas companies are still making lots of money, even in the current downturn. One of the main uncertainties is in the reservoir. They are huge. And not surprising, these things are in underground somewhere. We can't go and actually physically measure them. They're actually made of rock, they're not big open space. So actually knowing whether this is connected to that and various things on a limited budget with only a little bit of information, there's lots of uncertainty. And they have to handle that uncertainty. But the problem with all these different disciplines that I've been mentioning have different worst cases, and that's the thing to remember because the economists, they're in charge of the project really, the number crunchers, bean counters. They're worried about the smallest recoverable reserves because they want, there's a certain amount they want to spend and a certain amount they want to recover to make money. So they're worried about the P90 profile they talk about a lot, and that's a 90% confidence limit that it will be like this or bigger. So it's quite a conservative, quite small value. They're quite conservative on that. But it's not necessarily conservative for every other for all the engineering disciplines. For example, hydrates and wax is normally avoided by keeping it hot. So what if in a system of a hot reservoir and a cold reservoir blended together in a pipeline, what if we're worried about low temperatures, what if the coldest reservoir is the biggest? Well, these guys go, Martin, bigger reservoirs are better than smaller reservoirs. And no, but what if my cold reservoir is bigger? We end up producing a lot more from it. My pipeline is now colder. I'm now closer to the wax problem. So we have to think more than just, I'll design to this P90, that's the worst case, everybody. It's not, we have to think about, what's my worst case? Ditto for the other engineering disciplines. Corrosion engineers are worried about high temperatures. So they're the reverse. Higher temperatures mean higher rates of reaction, so the corrosion rate is quicker. Pipeline mechanics even more complicated. We'll go into that. Lots of back and forth between disciplines to say, does this look sensible? Is this what we want to design for? Okay, so timescales. Different problems have different timescales. So there's pressure surges. These are things that are happening when we're slamming a valve shut, and pressure surges are moving around at the speed of sound around the system. Really, that's in terms of tenths of a second that we need to resolve that to get it properly. There are multiphase flow issues, depressurization and slugging. That happens in tens of seconds. That big, horrible mass of wax, black, yucky stuff, okay, that tends to happen in weeks, unless it's really, really messed up. Okay? It tends to happen in weeks or maybe months. Corrosion, well, the typical unit for corrosion is millimetres per year. Okay, I'm not going to get too excited about that, but life of field, of course, we're worried about how the system is changing over life. That's happening over decades. It's numerically what we call a stiff system. I can say it without chuckling now. I used to not be able to say that without giggling, but it's a problem that we're worried about decades, but we need to model in tenths of a second. So I need tiny, tiny, tiny little steps and go for a very long time. So can it be done in one simulator? Well, it's not done in one simulator at the moment. There are different classes of simulator, and they do overlap. A life of field simulator, what we call a transient simulator, but of course in the grand scheme of things, these are all transients, they're just in different timescales. And a surge simulator, normally a very specialist one for pressure surface. How long can we wait for the results? Well, this life of field simulation that I was talking about, really the whole thing must be done within a few hours, otherwise it's useless to me. You know, going back to that joke I mentioned about, you know, it takes 3 months to work. It's no good. It's going to do it within an hour. So each time step, so every month updating and doing a new time step, must take a few seconds, and I've got to optimize. That's the 1.7 quadrillion scenarios I've got to optimize. Yeah. As far as the customers is concerned, yes, it's the optimum. No, it's not true. I just need a quick and simple way of having a good way of choosing this allocation or whatever it is problem, because I need to do this quickly. Okay, so requirements. During design, we need speed, stability, and accuracy. Okay? No matter how fast you make it, it will not be fast enough. We made our simulator. It was about 10 times faster than anybody else's simulator, and still people were going, well, can you make it faster? You know, because they just use it for bigger and more complicated problems. So no one's ever going to say, this is a bit too fast for me, actually. Oh, maybe a contractor who's on an hourly rate. Maybe need a contractor button that slows it down a bit, so they get to charge more hours. But in general, no. Network simulations must survive flow reversal, or all kinds of weird stuff that I've talked about in one of my other papers, actually. Flow reversal, negative pressures, which sounds weird, but it's a numerical thing rather than a physical thing. Ill-conditioned objects. These are things that the network simulator must survive somehow. That can happen because of the numerical methods for balancing these networks. Flexibility has got to be easy to use, nice graphical user interface. User-defined logic, so we can go in there and change things to our own particular way to model something, new technology that hasn't been thought of when we develop the thing. Getting results out from multiple disciplines, just make it easy for the flow assurance guy to get their temperatures out is okay, but actually then there's the pipeline engineers and the corrosion engineers, they need different data, it needs to be easy to get their information out as well. Checking the inputs and outputs, fast fit-for-purpose optimization methods, I'll just leave it there, but again that's something I can talk a long time about. And one thing that's very, people get quite excited about in the industry, periodically, it comes and goes, is connectivity with databases, to dump the data out so that somebody else can connect to their model to that database. And there are but also connectivity with other software as well. There are pros and cons on that, and a practical thing, but if you want to sell software, then it's a good feature to have, even if you don't think it's practically useful. And finally, for all simulators, particularly if it's going to be used in the engineering world, begin with the end in mind is a good thing to have in mind, or in the design world it's called top-down design. Think about what the end, who's going to use it, how do they work at the moment, what problems do they have at the moment. There's no point in solving a problem that they don't have, or they don't think they have. Or if they have much bigger problems that some other piece of software solves, and your problem that it solves, okay, it doesn't do as well, but it solves that bigger problem. So thinking with that is critical if you want someone to actually use that. And if you want to change the way that they work, and no problems in doing that, but you're going to have, how do you manage that change? This is now getting into management consultancy stuff, and I apologise for that. But actually talking to people and helping them change management, some sort of training, some sort of consultancy as well, is very important and critical actually if you're going to get people to use this thing. Because the problem is, this is used quite a lot in the industry, is this cartoon here. You're selling the world's greatest wheel, and these guys, with their square wheels, they're going, no, I'm too busy. I've got too much hard work. It's a very difficult thing. It sounds obvious, this guy, but, well, it's obvious, you need round wheels, but no, I'm too busy because I'm using these square wheels. But in the words of the head of one major oil company, when I showed them Maximus once, they said, this is exactly the way we should do things. However, this isn't the way we do things. Okay, well, that's giving you something to think about. If you want any, well, we've got some time for questions. Sorry, I don't know whether I've overran or not.
Yeah, maybe 5 minutes. Yeah.
Sorry. Any questions now? Questions? You can catch me over lunch. I'll be here.
Yeah.
In my previous life, I was an engineer in the industry in brochure and something with mechanistic models
I noticed you nodding a lot.
and like some bridge correlations, etc. I wonder, that was about 15 years ago. So I wonder is what about the modeling using stochastic equations? So it's trying to involve the uncertainty to very well explain into the model itself. I remember my experience, I always work with deterministic approaches.
Yeah.
I'm wondering is now with stochastic PDEs, etc.
I have done that on certain things. But at the moment it's very case by case. I classify the way that most things are designed in the oil industry is they add as many design margins as they can think of until they can't afford it, and then they take a design margin away. Okay, can we afford it now? Okay, we take a design margin. We've still got these other 3 design margins. But does this make any sense? And on one project, we showed them, because they were so confused, they went to a generic engineering company who did all these design margins, and the oil company went, yep, I agree with that one. 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 Yep, I agree with them all, they're all good. Okay, well when you add them all together, it means you need the world's largest injection system for this inhibitor. No one's ever seen anything like this. This would be something, you know, that the Discovery Channel will be doing a documentary on the enormity of this injection system. Oof. Okay, what if you take them all away? If you take them all away, you don't need you don't need to inject it. Because, so, hang on, it's either the world's largest or I don't need one. Well, so that's when a stochastic approach came in, because, well, okay, what's the probability distribution of this uncertainty and this one and this one? And then when you went up, it became for 99.9% of scenarios, sounds like half of 99% of scenarios, you could get by with one that was a quarter of the size of, quarter of the design flow rate of this world's largest one. So it stopped being the world's largest one. And then they were happy with that, they convinced themselves. Importantly, it would work for 99.9% of cases, and we said, in the event of that 0.1% of cases, this is how you have to operate it. It's not, you wouldn't have hydrate blockages, you just need to start shutting in high water producing wells. So it would be painful, but it wouldn't be as painful as a blockage. It just means you can't produce as much gas as you would if you'd have bought the largest injection system. So there are opportunities like that, but generally for everything, no, I think it's they're quite happy with the slap on those design margins, it's too expensive, yeah. And so, it's not very satisfying as an engineer.
I think you can just move